In this video, we are going to solve a problem based on circular motion involving a mass spring system. Let us read the question. A spring with spring constant K and natural length R0 is attached to a mass M with the other end fixed at a pivot, as shown in the figure. Now, if you look at this figure, which represents the schematic diagram of the problem, we see that there is a pivot or a fixation point or a shaft which holds the system in place. Now, do not confuse with two springs or two masses. There is actually one system in this figure, but in two different states. At this state, the system has not experienced a circular motion yet, while at this state, the system experiences a circular motion. That is because of whirling the mass, okay? By whirling the mass and thus giving it a tangential velocity or tangential speed. Notice how the spring stretches in that particular instant. Let us continue. As the mass moves in horizontal circular motion, determine whether the spring is stretched or compressed. Find its elongation and calculate the maximum speed the mass can reach before it can no longer maintain its circular path. Assume no damping effects. Okay, so the question has three parts. The first part asks us whether the spring is stretched or compressed. Well, if you look at the geometry of the problem, indeed, the spring gets stretched. Okay, the spring gets stretched. But why is that? Well, that has to do with the nature of the centripetal force. First of all, we know that the centripetal force, Fc, is a net force, according to Newton's second law, and must always point toward the center, always directs toward the center. Okay? Furthermore, the centripetal force is a situation force, or form dependent, in other words. What I mean by that is that the centripetal force can take in the form of tension, gravity, friction, spring force, and so forth. In this case, it takes in the form of spring force. Okay? Thus, the spring force must provide the centripetal force in that particular circular motion. But how? Well, the only way to let that happen is when the spring gets stretched. Because when the spring gets stretched, it tries to pull back the mass toward the center by means of a force. In this case, it is the spring force. Compression, on the other hand, it does not make any sense, because if we compress the spring, then the spring will try to push us back, okay, by means of another force that, of course, points toward outward, okay, outward the center, which does not make any sense. That is not the centripetal force. The centripetal force must always point toward the center, okay? So, in essence, the spring gets stretched. Okay, that's the answer to this part. The second part asks us to find its elongation, an expression for its elongation. Well, to do that, first of all, if you measure the distance from the pivot to here is R0, which is the natural length of the spring. Now, this extra distance due to the circular motion is actually x, or the elongation part. Now, notice that the sum of these two equal to r, the radius of the circle, or in other words, the full length of the extended spring. Okay? This equation is a key. We have to save this. All right? Okay. Now, how can we find the elongation? Well, by convention, we take the positive sign of any force that acts toward the center. So in that case, Fs, the spring force, is equal to the centripetal force. Now, if you remember that Fs is actually Kx, and Fc is m r omega squared, where m is the mass of the object attached to it, omega is the rotational speed of the system, and r is the full length of the spring at that instant. Okay. Notice that I have taken the positive part of the spring force, because according to Hooke's law, we know that when we try to stretch the spring, the spring tries to pull back the mass toward the equilibrium by means of compression, and in compression tries to stretch it back, so vice versa. But in this case, by convention as well, we knew that any force that acts toward the center is taken as positive, okay? Pay attention to that. Now, we know that r is equal to r naught plus x, so we're going to substitute this into here. See what we get. Kx, because we are trying to find an expression for x, or the elongation, is equal to m r naught plus x omega squared. Okay, which basically is kx equal to m r naught omega squared plus m x omega squared. Okay, let's get rid of all of this. Now we have, and let us move this part to here. Okay. Now what I'm going to do is to bring this to here. Okay, so kx minus mx omega squared is equal to m r naught omega squared. Solving for x, or the elongation, gives us, first of all, let's take an x as a factor out 1x, so we get k minus m omega squared is equal to m r naught omega squared. Okay, so that means if we solve for x, what we get is that x is equal to m r naught omega squared divided by k minus m omega squared. So this is the expression for the elongation of the spring. Now, notice that this equation tells us a lot of stories about this type of motion. So the elongation is positive as long as k is bigger than this factor, m omega squared. Look at the denominator, okay? So the extension or the elongation is positive, okay, as long as k is bigger than this factor. In fact, as this factor, m omega squared, gets closer and closer to the k value, to the spring constant, this extension tends to go to infinity, which in theory it makes sense, but in practical, no, it does not make any sense at all, okay? Because you have to know that in real life, in nature, every type of spring has its own final elongation, or in other words, every spring has its own elastic limit, okay? So there is no just x, but x maximum, okay? So every spring has its own elastic limit, x maximum, okay? You cannot just play with it and extend it infinitely and boundedly as much as you want. You cannot do that, okay? It's not allowed, because either the spring will basically collapse, it breaks, okay? And eventually the circular motion fails, okay? But that's for the elongation part. So in summary, we can say that the extension or the elongation primarily depends on the rotational speed of the system, omega here. Mass and k are constants, okay? So that's for it. Okay. For the third part, It asks us to calculate the maximum speed the mass can reach before it can no longer maintain its circular path. Let us introduce x maximum, because we have to do that to find the maximum speed. If we do not introduce the maximum elongation, then in theory, the spring can go forever, can be stretched forever, and thus the circular motion may just continue, but not in the way that we expect. But nonetheless, if we do not introduce this maximum elongation, this elastic limit, so as to speak, then the maximum speed would be infinite, which it does not make sense. Okay, so let us write the equations again. The Newton's second law, the net force. We know that again, Fs is equal to Fc. Okay, now this time you write Kx maximum. We assume that the spring has its own maximum elongation, a limit, an elastic limit, that is equal to mv squared divided by r. Now r, we know that again. R is equal to r naught plus x maximum. Watch out for it. Okay. Now we can solve for the speed, or the tangential speed. Okay, that's easy. So let us multiply both sides by r and divide both sides by m. What we get is that v squared, okay, is equal to what? K over m r naught plus x max times x maximum. Okay. Now if we take the square root of it, we get the maximum speed. Okay, so let me just select this and bring it to here. And now if we take the maximum speed, in other words, we get v maximum is actually equal to the square root of k over m x maximum multiply by r naught plus x maximum. That's the final expression for the maximum speed the mass can reach before it can no longer maintain its circular path. If you overcome the elastic limit, this x maximum, then you cannot maintain the circular motion of this system. So for that to happen, we have to know the maximum elongation, the elastic point of the spring. Then, substituting the values into this equation, we can obtain the maximum speed for the mass can reach, all right? And notice that this speed is the tangential speed, all right? So if you try to overcome this speed, any speed, if bigger than v maximum, then what happens? The circular motion fails. Okay, the circular motion fails. The spring may break, the mass may fly away. Okay, that's it. And that's it for this problem.